address. So
you said there were 3 different kinds of templates.
Yeah.
How many was it detected with just one?
That was detected with the R template, which is typical for short GRBs. Now I forgot to say this. The R template is the one for the short GRBs, the moderate or medium one is for the long GRBs, and now we have soft.
I have a question to the energetics of this detection. You showed the spectrum, and you gave the fluence in X-rays and gamma rays. And from that you can take the known distance to the...
From the gravity, we know the distance from the gravitational wave.
Calculate the luminosity.
Yes.
How does it compare with the 3 solar masses converted into gravitational waves?
The luminosity is much lower, or it's lower than compared to the E of the short GRBs seen by Fermi, but in the new version or the latest version of the paper they have shown 2 examples of short GRBs, detected short GRBs by GBM, which have a comparable luminosity. In principle, it's the lower end of the luminosity distribution of the GRBs. So it's outlier, but there are other GRBs with this luminosity. Yeah.
So, I have many questions. I think it's exciting, but I'm going to ask one. When I saw the paper the first time, the thing that really struck me was that before the peak, there's an obvious dip there. No one seems to talk about that.
Yeah, but these dips are, if you look at longer time scales.
Because you said, when you showed all the detectors, right, you pointed out to the fact that all of them had an excess after. I'm talking about, but if you go to slide before, yeah. Is it this? No, or anyway, you were saying that all of the light curves have an excess after the light of
light blue timing. Yeah.
But if you look, they also have a decrease just before it as well.
And you can see the decrease in the sun dark light curve.
Right, and then it's clear.
And you can see also these some decreases here.
Sure, but that's the big one.
Yes, it's significant. In the paper, they
talk about
this, of course.
Because it's wild as well.
But this is only for showing as the detection is on the basis of the targeted search, not on this. It's only showing what are the detectors showing. But the detection claim of a detection of something is from the targeted search, of the template spectrum, not from the. It's in the appendix. Okay. They changed it from the first version. This was in principle in the beginning. On the latest version, this discussion is in the appendix, only for an add-on. But they.
You mentioned that in 27 events in 3.5 days or so, have they been found with the same coordinates, assuming for the LIGO event, or how were the coordinates?
They did the search with all coordinates in the sky. And the interesting thing, from these 27 events, 24 are in the characteristic different from the one which was found. And they found some of these 27 events near to the A exit. And they found that the background fitting is worse, but they didn't mention it in the paper. In principle, they are better. The faults are not, but they didn't include it in this calculation because it was done afterwards. They only described what the pipeline detected at the time of the event. The pipeline was prepared before the event, so they didn't do changes afterwards to improve the significance.
Were these events also predominantly coming from the backside of the main illuminated detector?
I don't know.
Because this whole structure reminds me of something that's seen a long time ago in ACS, right? When we had these spurious events on very high rates, which produced typically full saturation, and then this very bright 15 millisecond event. We thought eventually that it's associated with cosmic rays on the detector. And so 27, with the 27 events, that would quite a lot.
From the 27, because you're getting this probability.
Yeah.
But from the 27, most of them are different in characteristics. So it's in principle better than this 27.
Okay. So how many are there which are similar to this event?
It's 3 more.
So,
Not so bad.
it's about 1 a day.
Sorry to harp on these numbers, but it's still obvious to me why you can do this false alarm rate check using the actual spectral shape that is derived from this detection.
Yeah, it's
Why
only
do you
the,
do the exercise? I mean, if you solve moderate and hard, but now solve moderate and hard meant
yeah.
the GBM.
They used the template, this is post-trials estimate. Yeah. So they found something with the hard spectrum, and then they looked how often are we finding a similar hard spectrum dip or excess in the light curve. There's nothing more.
The actual event resembles more closely with the solve. The actual event looks more closely like the solve one.
No.
The outlaw left hand is.
No, if you look into the detector, it's not so. How was it? So the mean end, it's interesting if you look into the energies, you can see. Because of that, I've shown you the dependence of the detector response's energy. You can see in the VGO, the excess is seen up to 5 MeV, where you have already a high effective area. At lower energies, in the sodium iodide, at high energies, because you have less effective area, it's going down a little bit. At lower energies, you are shielded by the housing. So it makes sense that you have, and also here, having a highest spin up to 400 kV, where as I have shown you before, the effective area is already dropping at 150 kV. So having a high band at this energy means it's hard, and not soft.
See the light curve of the detector used for the spectrum. You said you only use one detector.
Number 5.
I mean, the obvious question is that the one with the highest signal out of the...
No, we selected, the only cause selecting number 5, also it doesn't have the highest significance. It has only 1.68.
But that's the one which is more on axis.
No, this one, yeah.
But then why doesn't it have the highest signal?
Because
Oh, yeah, sorry.
the possible region where the signal can come from is very broad. And as you have seen, you can, for a hard event, you can get response from the background. So this normal GBM method selecting the detector with the lowest angle is maybe, we are always doing it, but this is a very unusual case. So.
All right, I think we should switch over to that now.
Yeah, of course.
Yeah, so thank you. So I'm here to present some counter arguments to the paper just discussed. So I think this is very good science because we discussed the counter arguments openly and objectively. So I talk about our paper on behalf of Johan, which is leading the paper. He's also the GBM PI, and also J. Michael Burgess from KH Sweden, and Shevchenko Potavier from Paris. So before have a look into the data about the Fermi GBM light curve, and we want to argue that it is less possible to be an astrophysical event. So this is the story. So most of you have already heard about it. So the gravitational event GW 150914, the first announced by LIGO, which is the first detection, direct detection of a GW event, and with a 5 sigma significance. And the GW source is about coming from about 60 solar masses binary black hole merger, and so those are two black holes. So theory predicts that black holes should be black. So this is the basic assumption. And and no electromagnetic counterpart has been observed except for the claimed event from Fermi GBM. So we already have a lot of information from this statement because we have plenty of space telescopes out there, and none of them have detected anything. So so that we analyzed the Fermi GBM data to do a sort of double check, and we looked at the time interval specified by the Colonna paper, and we found no significant signal. And now our paper is now accepted. We published in MJL. And so this is the raw data come from the, this is the raw data from that time interval. And this is CAM.
From detector 5, which one was it? Which detector?
11.5.
Okay.
11.5, okay. And so the blue curve is the total counts in that time interval. And so, and then we show in red and orange that our fit, I will talk about it later in the later slides. This is our fit to the background, and also the background has source. And you can really see that the source is only very, very little above the background. So it's very weak if there's a white source. And to further show the insignificance of this excess, we plot in green histograms the residual of the source, which is the source plus background subtracted by the background. And we beam it up because it is too small. And the here also is a dashed vertical horizontal line, which indicates where the usual official GBM spectral analysis method breaks down, which is fitting by chi-square, because there is so few counts that you cannot approximate the posterior by a Gaussian shape. And then we have to use the Poisson statistics, and together with the so-called Coulomb interval, which is also plotted here in the green and blue error box. And so we would argue that the statistics really matter. So here I showed you the plot from our paper that we first simulate different count rate, and then we try to recover the count rate with two different methods. One is the usual least square fitting by chi-square, and actually chi-square is an approximation. It's directly assumed from the Gaussian distribution, and also from our method, the Poisson, using the Poisson statistic. And you can see that below about 7 to 6 counts, the deviation is becoming worse. And the Poisson statistic can always recover the true rates rather the chi-square statistics just give you completely wrong answer because there is not enough count, and the Poisson distribution is not symmetric. It doesn't look like the Gaussian in a low count regime. So in our analysis we have to use the Poisson likelihood by maximum likelihood estimation, and this is also known as the cache statistics, and which is shown here. This is the likelihood, and this is the log likelihood we have to maximize. And so the M is the model count rate, and this is the source count rate, and so this is basically this equation we are using. And because we have fit the background polynomial, so as Andrew has already discussed, so the GBM analysis, we have to first extract the source interval, and then we select background intervals, which is outside this source in the time interval, and then fit the polynomial to the background. So then this is how we determine the background, and then we further extrapolate the background into the source interval. And because in our approach, because we already know the background estimation, so we can use this information in the Bayesian method, in the Bayesian approach. So this is the background, and this is the background polynomial we are fitting, which is of course time dependent, and also theta is just the polynomial coefficient. And so if we integrate this, we get the background rate. And so we can incorporate the background model into the likelihood we are fitting the source. So we want to clarify one thing, that the source model, the source statistics and the background statistics incorporated in this equation is not the same. So the source is always Poisson. But the background, because we have already fit a background polynomial model, and we can obtain the error bars on these parameter vectors. So when we do error propagation into the source plus background model, the error bars on the background is Gaussian, because the Gaussian approximation of error propagation. So we have to use the statistics which incorporate Poisson data and Gaussian background, and this is embodied by the in the PG set, which is so-called PG set. This is the equation, and so this is the equation we have to minimize when we try to determine the source, the parameters of the source in case 1. In contrast, the official GBM analysis software ARMFit, they assume no variance in the background because they just assume the background is perfect after extrapolation into the source interval. So there is no error considered in ARMFit. So these are the two. So this is the mathematical difference between the two methods. And so first we have to validate our method. So we try to simulate. So by the red side here, we simulate a source. So this is just a power simulation of the power law model. This is the amplitude, and this is the power index. So we have simulated a model with a power index minus 1.4, which is typical for power fit of source GRBs. And the left panel shows a bigger and more luminous source, and then with a dimmer source, and with no source in total. And the green contour and the total contour are the fit results obtained by our fit and our PG set method. So you can see that when the source is bright, okay, both methods are correct because, well, it's bright. We have so many counts, so it doesn't matter for two different statistical approaches. And so we can recover the source. But if the source is dimmer, and you can see, sorry, I fixed up. So the green is our method, the purple is our method. And you can see that when the source is dimmer, our method can detect it, the contour of the error contour of our method can encompass the true source location, right? But the unfit method always predict a brighter source. And this is even worse if there is no source altogether. So we simulate no source. So that means we just put in background, and then we fit the source interval with both methods, and immediately our method says that, okay, there may be something, but it is very, very deep and very, very soft. So basically nothing. But unfit always return almost the same result. And then we fit the this Planck event by the two methods. So these are 10 occasions because in the quantum paper they do the analysis along the LIGO arc because it's very, very large. So they divide it into 10 positions and then do the analysis repeatedly. And so we do the same. And this is the unfit based analysis result, and this is our PG set based analysis result. And you can easily compare the fluence inferred from these two fits. You can always see that our results return always 2 to 3 times dimmer fluence than what claimed. And also the power indices from our PG set analysis is always softer. And so this seems to contradict the claim that it is a short GRB, because short GRB are also harder than long GRBs. But we find something interesting. And so, what the spectrum really looks like. So this is the model we fit. This is just the time interval before the source, and this is in the source. So you see the background contribution and the source contribution here, and then this is after the source. So this is the time dependent and spectral dependent model we have fit, and the result is this one. And again, the blue is just the total count from only one detector, detector number 5, in 10 kV from to 1 MeV, and the red curve is the background fit. Is what we have fitted in the first place. So this is the background, and the contour is just because it is just from the different samplers of the Bayesian network. So we do multi-level. And then we fit the background plus source model with our method, which is called MLE fit, and this is the yellow data point here. So you can see it is completely consistent with background. And this is the RMFit result I repeated. I used the same procedure as the Colombian paper, and then I get this by the usual spectral analysis procedure of fitting a short GRB. And this is from the VC paper result because they use more detectors. And I have to admit that some of the procedures we don't really understand. So, but our result are close. Using RMFit, we always over-predict the count rate in the light curve. But using the Bayesian approach and fitting the source and so putting the source and the background information at the same time together, the mathematics tells us that it is just indifferent from the background. And also we try to look at this event and compare this event with adjacent background time interval. So we do the analysis using adjacent time beams. So this is the result, this is time, and this is the power index. And you see 10 data points for each time beam because we repeat the analysis using the 10 position on the LIGO line. And you can see spectrally it is indifferent from the background. And actually, what this spectral index really looks like, it actually looks like the delta below, which is background.
Are you going to say there's an EM counterpart 5 seconds after the?
Yeah, I don't know. No one has done analysis on this, so maybe. But this is just NI5. So we can also try to compare so we have two hypotheses. One is the new hypothesis that there is only background, and the other hypothesis is there is source plus background. So we can compare these two models. This is just Bayesian model compare. And so we try to do this compare this using the claim signal, and this is the result. So you can see here this is NI5 and this is BGO1. So and the green histograms here are the Bayesian posterior distributions, and the yellow may be very difficult to look at this one. It's here. The yellow is the mean. So you can see it is very asymmetric, and the mean is here, which is perfectly compatible with the background. The background is again the blue curve here. And if we simulate a burst, that means we simulate a source. And so the method should prefer the source plus background model, right? Because we simulate a source plus background model. And this is what our model can relate. It prefers the source plus background model, and the Bayesian posterior distribution is a little more symmetric, and the mean error value is here. And so our method can predict a source, a simulated source, even if it is weak. But using the signal from the GBM view data, we find nothing. And we also take a step further to compare to the real short GRVs. And so these are 58 short GRVs taken from the second Fermi GBM spectral catalog. And so this is the difference in the fluence and difference in the index by comparing to the two different analysis methods. So you can immediately see that, well, using our method, it always returns a softer and dimmer spectral shape for real GRVs. These are real short GRVs. And the 10 stars are 10 spectral fits from the 10 LIGO art locations extracted from the quantum paper. So you can immediately see that, well, it indicates a huge difference between fluence and spectral sharpness, spectral hardness values between the two methods. And further take two more examples from the which are detected from Fermi. So these two short gamma rivers we show here have very similar differences with the 10 LIGO art positions, which shows that there are some systematic shifts between the two methods, and this we should be considering in the analysis. And then we compare the Fermi result with the integral result. So remember the integral team report no detection from the SPI-ACS. And so we can just simulate the significance in the, so assuming there is a signal in Fermi GBM, and then we can just extrapolate and simulate. Actually, it is not extrapolating. SPI-ACS has roughly the same energy coverage as Fermi GBM. And so we can just simulate the significance that ought to be seen in the integral SPI-ACS. And this is the result. Using the claimed detection spectral parameters, integral should be seen everywhere larger than K sigma, but they see nothing. So this is very interesting. And we also saw here this is a very complicated plot, but this is just the significant map, and the 10 crosses here in red are the expected significance mapped to the integral map by the RMZ method, and the green one are from our PGZ method. So they are 10 crosses because they are 10 LIGO locations. And you can see using our method, we can predict we can predict much lower significance in the integral SPI-ACS, which is consistent with the non-detection. And then we further use two more Fermi detected short GRVs, which is shown here in boxes. So we can see maybe we have found maybe this is the reason why Andreas just talked about that for some Fermi short GRVs, integral is we see in Fermi GBM, but integral didn't see it. So maybe it is the reason. It is because they are dimmer, and because they are dimmer, our official method returns the wrong value, and so maybe it is completely compatible, the two results, just because the mathematics we are using are incompetent in drawing that conclusion. And so these two GRVs are extracted from the Fermi detected short GRVs, which is from the 20% dimmest population. So these are dim Fermi short GRVs. So I left my conclusion here, and so we have to conclude that the spectrum of this 10 GBM event is softer than typical short and hard GRVs. This is for sure. And then what we can also say is the spectrum is consistent with typical background spectrum as measured by the Fermi GBM. Because we actually, J-macro convergence did somewhat fitting on the background intervals when we did not report in the paper. And also, the background subtracted fluence of this time interval is actually consistent with 0. So our method is more consistent with the non-detection of the integral SPI-ECS result, and also actually confirmed by an independent paper. And so our result is consistent with the theory that black holes are flat. So no finding is needed. So actually, why we feel necessity to write an anti-paper is because we think that when we are claiming a discovery, so that in this case the existence of an astrophysical signal, then the first goal we have to do is to reject the new hypothesis. That means we have to reject, we have to show that it is not consistent with background. And in which case, if it is only background, then we don't have to fine-tune any existing models. And also, we do not have to lower our publication and press release standard from 5 sigma to 2 sigma. Right? So I'm happy to take any questions here, and I leave my 2 favorite quotes from the final here. Thank you.
Questions?
Could you please go back to the slide where you showed your method? So you validate your method, one of the first 4 slides or so.
Yes.
What is the reason, and does it worry you that you seem to be able to measure a very good constraint on the spectral index, even though there is no source in the rightmost?
Yes. Yes. This is because the standard analysis procedure is this. We just